So if you remember, I had said that the periodic table was designed to group elements by their chemical and physical properties. So now that we know what chemical and physical properties are, let's look at some of these and their orientation on the periodic table. So boiling point, this is a nice chart that shows how high the boiling point is of different substances on the chart. And you'll notice that most of the substances in red have higher boiling points than all of the other substances on the periodic table. That is a specific group of elements called transition metals, and they exhibit high boiling points there. And then you can also see that some of the yellow ones have really high boiling points. So these are also considered metals. So you can kind of see that these are grouped. All of these other ones kind of over here, they have really low boiling points. These have lower boiling points as well, and they're grouped this way on the periodic table. All right, here's similar chemical properties. So your alkali metals, that's going to be these guys right here. Your alkali metals in this first row are actually explosive when they react with water. So that's a really cool chemical property of your alkali metals. So they will all kind of do this. Your halogens, another group of stuff that we're going to talk about, tend to be reactive gases. Reactive, sometimes they're liquids too. Reactive gas, liquid, or even solid. Hydrofluoric acid is a very dangerous acid that you might have seen popularized in Breaking Bad, where they use it to eat flesh. So this is a very highly corrosive chemical, and most of the other chemicals in that row tend to be highly reactive and or corrosive. So when we work with hydrofluoric acid in the lab, we always use special gloves to make sure that we don't spill any of this stuff on us, because it will burn your skin. Okay. Which leaves us to this fun illustration of the different elements on the periodic table. So now you might understand a little bit more what this person is saying. We've got our alkali metals over here. Alkali metals. And this person had labeled these as badass because they explode. So now you'll remember that. This was the terrible one. It's very reactive. So we've got to be careful of that one. Most of these other metals that they've kind of labeled as stupid and boring, they're relatively inert. They don't do very much. So I imagine that might be what's going on. And then this down here, yawn, I think that's because we don't study those in chemistry very much. But this is uranium. Uranium has some interesting history, which is maybe why they have dictated it as worthy of notice. Okay, so anyways, that was just for fun. Okay, so here are all of the different areas of the periodic table that I'm going to ask you to know. These are nonmetals. I'm going to ask you to be able to identify nonmetals. Those are the ones in blue. Metalloids. Those are the ones in purple. Your main group metals. Those are the ones in pink, which are essentially metals that are not transition metals, which are your yellow ones, okay? I'll ask you to distinguish those. Also, your noble gases. You will need to know that's just the gases in that last column on the periodic table, in that last group. And these are your halogens. These are also important that I'm going to ask you to know. These tend to be gases. Sometimes they can be liquids, sometimes they can be solids. They're also important. So we're going to discuss all of the different properties of all of these. Okay. So metals and nonmetals have different characteristics. We're going to go over these. Metalloids are kind of somewhere in between your metals and nonmetals. Oh, okay, there we go. So these are your unreactive gases. We're going to talk about these in another slide. Okay, so let's look at our metals. So this includes all metals. So your main group metals, your alkali metals, your transition metals. Metals tend to be relatively hard elements. Some of them are malleable. So think about like gold. If you've ever seen gold, you can actually like scratch it with a fingernail versus iron. Iron's a very heavy, solid metal. You definitely can't scratch it with your fingernail. Even some other metals, such as mercury, it's the only one on the periodic table, is actually a liquid at room temperature. So we have different hardness variabilities, but the majority of them, copper, zinc, iron, that sort of things, tend to have high hardness. They also are decent conductors. So what's interesting about metals is they have this particular structure that lets electrons flow through them really, really easily. They are usually solids at room temperature. There's only like 2 exceptions to that. I think the one is mercury, and then gallium's also kind of close. And then these are also dense materials. These are relatively heavy materials. And oftentimes you might hear the term alloys used. These are mixtures of metals. So when you mix things, you get a different terminology for them. So things like brass, bronze, steel, we use these in construction a lot, are a mixture of metals. So brass is copper, and it's mixed with zinc. So copper and zinc mixed together gives you brass. Bronze is copper and tin mixed together. And steel is a lot of things. It's like carbon and chromium and all kinds of interesting things. It has more than 2 metals in steel. And then we've got all the different types of steel. So it's an interesting metal, or metal alloy. Okay, so here's kind of what's going on in the metal when it's conducting electricity. So this electric field that's applied is when the electrons start moving throughout the substance. So these here are your metal cations, these blue things. This is without the electric field. You can see the electrons are just kind of going every which way. And then when the electric field gets applied, we have this positive and negative charge. The electrons start flowing through them. So this is why they conduct electricity very well. So you might hear this referred to as a sea of electrons. And metals have a particular structure that lets them do this, where the electrons can move freely throughout the metal ions, or the metal atoms that are in the structure. Okay. Transition metals. So this encompasses these yellow metals down here. Transition metals, what's unique about these is they have multiple charges. So we had discussed how each group here, this is a positive 1, this is positive 2, tends to form specific ions, right? This will be a -1, this will be a -2. But transition metals, they're strange because they can have different charges on them. So this is an example of copper here. You can actually see these look very different depending on their different charges. So copper 0 is the brown one, copper +1 is green, copper +2 is blue. They actually look different, they react differently as well. So this is what we call an oxidation state. These different numbers here. It describes the degree of oxidation, which is loss of electrons. Remember, in order to get a positive charge, we've got to get rid of some of our negative charges. That's how these things do this. So it describes the degree of oxidation of an atom in a chemical compound. So you might hear me refer to these numbers as oxidation states when there are multiple ones, or maybe oxidation numbers. Now, if you're looking at an atom that just has only one possible charge on it, it's just a regular ion, okay? This doesn't have more than one oxidation state. That is the only oxidation state of your hydrogen, okay? So please don't get these mixed up. Only your transition metals will do this. Will have more than one oxidation state. So you might be wondering why they can do this. I think it's kind of important to describe this because I don't like to leave students just kind of guessing at why this happens. So if you take these metals and you actually look at them in the atom.phys app on your iPad, you'll see some interesting things about these. So your transition metals often have these openings here. in an interior electron orbital. So normally the electrons that move are your valence ones, the ones around the very outside, but for some reason our transition metals have this opening inside the valence. And so what happens is sometimes electrons jump in and out of here very easily. So sometimes an electron can jump in and one can leave and you get a +1 state, or maybe like they both leave and none of them jump in there and then you've got a +2 state. So if you lost one, that would be a +1. But if both of them go, then that's a +2. And they have the ability to do that. So that would be these valence electrons here would be the ones moving. Okay. So let me know if you have questions about that. So different ones do this. So copper also has an opening, so it can do that too. So this one can jump, those guys can jump in there. Zinc has no openings. So I believe that zinc only has one oxidation state because it doesn't have these. Same with gallium. So you'll notice that the transition metals that do this have this specific chemical property that allows them to have more than one oxidation state. And that's why they're grouped together on the periodic table, because they have similar chemical properties like this. Now let's talk about metalloids. So metalloids are somewhere in between a metal and a nonmetal. They're not a metal, they're not a nonmetal. They're their own kind of weird identity, and they have kind of deviant properties. The more that you kind of progress this way across the periodic table, the more non-metallic character that an element has, versus this way, the more metallic character an atom has. So some important things to know about metalloids. They fall in this little green category here. There are very few of them on the periodic table. All right, only a couple. And these are questionable. They might be metalloids, they might not. Plus the color change. So these are probably the only definitive ones here. Okay. These things tend to be metallic in appearance, but they tend to be brittle, and they aren't the greatest conductors of electricity. They're only okay at it. So chemically, they behave like nonmetals, but they also have metallic properties because they can form alloys with other metals. And many of their chemical and physical properties are kind of somewhere in between. So here's one of these weird metals. This is gallium. If you notice, what's interesting about gallium is it has the ability to melt in hot water. So this is a metal. It looks like a metal, right? But it doesn't act like one. Metals should not be dissolving in hot water like that. And so if we take a look at where gallium is on the periodic table, gallium is here. It's not necessarily a metalloid, but it's really close to it, and therefore it has some, it has decreasing metallic properties. Another property of our semimetals, or sorry, our metalloids that's really important is the semiconductor. So semiconductors like silicon is a metalloid, it's in that category. Semiconductors are used in a lot of electricity applications because they allow electricity to pass through them, through that electron, through the sea of electrons, but they don't pass through it great, which is really important when we're looking at electricity conduction. So the problem with metals is, yeah, they're great conductors, but if you have a really good conductor, oftentimes you can short circuit stuff. So it's like too much electricity too fast. It's kind of like on overload. So think about the breaker in your house, right? The breaker goes off whenever you have like your hairdryer going and the oven going and like a bajillion computers going all at the same time, and they're all in the same room. You know, and you're using a lot of electricity all at once. Your breaker goes off because it's short-circuited. That's too much for it to handle. So semiconductors are nice because they tiptoe the balance in between a conductor and an insulator. An insulator, no electrons go through. And therefore, we have no electricity because electricity is electrons. Electricity is essentially movement of electrons. So whenever you have your electrons moving from one place to another, we generate a current, we generate electricity. And semiconductors let us do that. So they let us pass electricity through them decently because they have this small band gap. It doesn't require too much energy to do it, but it's not too much and it's not enough. And so things like your solar panels are made out of silicon and other types of electronics and your computers and whatnot because it's a great semiconductor. Let's take a look at our noble gases. Noble gases are in this last column here on the periodic table. These are very, very stable. They do not chemically react much at all. The reason for this is because they have a full octet. So remember that they have 1, 2, 3, 4, 5, 6, 7, 8 electrons around them except for helium. It's an exception. And so they're what we call inert. They don't like to react. So we use them in applications where we don't want chemical reactions to take place. So in manufacturing, a lot of time, especially sodas, that sort of thing, or just food products in general, they use inert gases a lot of times to bottle them because they don't want a chemical reaction to take place and destroy the food product. So a lot of times, bottling things, they'll use inert gases in order to do that. You also find your noble gases actually a lot in light bulbs. That's another interesting application of them. Halogens, that's this group here. So this is our group 7A, and these are reactive gases. These are quite reactive, well, not necessarily all gases. This is our chlorine here, and it's a gas at room temperature. This is bromine here, the next one down, and it's a liquid / gas at room temperature. It's kind of both. And then we have iodine here at room temperature. It's a solid, but as we saw in that previous video, it can easily sublimate and go to a gas. Your fluorine is also usually a gas. It's not pictured because it's very dangerous to work with because it's very highly, highly reactive. This one's extremely reactive, even more so than all the other halogens. Okay. So these halogens here like to form anions. We know that. They tend to form a -1 anion. And these are often sites of chemical reactivity in molecules. So things like your chlorofluorocarbons. This is, let's see here, CFCs. They look something like this. We've got carbon, chlorine, and fluorines attached to them. These are refrigerants that used to be used. They are now banned because they were so reactive. They were going into the atmosphere and destroying the ozone. So a lot of times when you see chlorine or fluorine stuck to an element, that's a site of chemical reactivity where chemical reactions will take place. Nowadays we use more HCFCs, and we're still looking at alternatives because they still have chlorine in them. They're still relatively reactive. Another application you might be familiar with for halogens is actually iodine being used as a disinfectant. So iodine will stay in your hand like this. It'll turn it bright yellow. But they actually use it in like hospitals and stuff. So this is a surgical scrub here, and it's got like 8% iodine in it. So it's used to sanitize things because it kills things because it's reactive. All right, so take this quiz here and see if you can answer this question and classify each of these elements as a metal, transition metal, metalloid, nonmetal, halogen, or noble gas. Remember, they can be more than one, so give it your best shot. So if we look at the periodic table here, our lithium's right up here. It classifies as a metal and also an alkali metal. An alkali metal is this first row here. It's our first group. Sorry, / column. Then our chromium right here, this is a metal, and it is a transition metal. our argon over here. This is a nonmetal. It tends to be a gas, and it is a noble gas because it has a full octet and it doesn't like to react with things. Bromine. Bromine's right here. So this is a nonmetal, and it's a halogen. It is a reactive gas. Okay, so that's that for that quiz.